Some of the same effects, but a little bit less dramatic, have also been seen to form after other explosive eruptions as well, such as the one seen from Mount Krakatoa, which is also in Indonesia in 1883. So the monitoring and the data collection that follows a few of the more recent eruptions has actually helped to get some of the insight on the magnitude of the climatic influence from these explosive volcanic eruptions. So monitoring that followed Mount St. Helens eruption in 1980, the eruption from El Ciclón, and the eruption from Mount Pinatubo have actually helped very much so. So from Mount St. Helens monitoring, the global cooling that was seen was only of about 0.1 degrees Celsius following that eruption, a quantity which could have really been caused by any other natural temperature fluctuation. So it wasn't very relevant. It didn't seem to have such a big effect. Also, 2 years of monitoring and studies that followed the 1982 eruption from El Ciclón, which was in Mexico, actually indicated that it had a greater global cooling effect than did Mount St. Helens. So the temperatures actually lowered about 0.3 to 0.5 degrees Celsius after this eruption, as opposed to 0.1. But this cooling effect did not have to do with the amount of material that was erupted, but rather with the type of material that was erupted. So El Ciclón actually didn't erupt as much solid material as did Mount St. Helens. Mount St. Helens actually erupted a lot more of this ash and debris. But El Ciclón erupted far greater quantities of sulfur dioxide as opposed to these fine ash debris. So the sulfur dioxide reacts with the atmospheric water vapor and it creates sulfuric acid droplets. These will remain in the stratosphere for many, many years and they will reflect the solar shortwave radiation. So in turn, by reflecting the solar radiation, they will contribute to lower the temperatures of the troposphere. A similar effect was also observed after the Mount Pinatubo eruption in, I think, 1991 in the Philippines. So in this case, it ejected 25 to 30 million tons of sulfur dioxide into the stratosphere. And so scientists then understood after monitoring from both of these eruptions that it really isn't the volcanic debris, but rather the sulfur dioxide amounts, which are responsible for the volcanic clouds which cool the atmosphere subsequent to the eruptions. So, although the impact on global temperatures of these explosive eruptions, like the one from El Ciclón and from Mount Pinatubo, is relatively small, as you can see from the graph here, the cooling effect could alter the general pattern of atmospheric circulation for a relatively limited period of time, which in the long run it could ultimately alter the weather in certain regions for years. So it is thought that volcanism also has effects on global warming different to the one that we talked about in the last slide. So for example, in the Cretaceous period, which ranged from 145.5 to 65.5 million years ago, and which is when the dinosaurs were around for the most part, was one of the warmest periods of Earth's history. During this time, for example, there were coral reefs that formed as much as 15 degrees closer to the poles than they do today. There were coal beds that were starting to form in high latitudes. Greenland and Antarctica both supported tropical forests, and the sea level was about 200 meters higher than it is today, so very warm. And it has been speculated that the temperatures that were seen during the Cretaceous period were associated with an increase in the amount of carbon dioxide, which, as we have learned earlier in the lecture, would act as a layer that contributed to the greenhouse effect by absorbing the long wave radiation from the Earth. But where did all of these carbon dioxide come from in the first place? Why was there so much of it in the atmosphere during the Cretaceous period? Well, for that, many of the geologists think that a possible source of this carbon dioxide was from volcanic activity. So as we learned in chapter 5 as well, carbon dioxide is one of the gases emitted at volcanic eruptions. And now, there's enough evidence that suggests that during the Middle Cretaceous there was really high volcanic activity. So there were large lava plateaus possibly associated with large mantle plumes that were at depth, and that there was massive outpouring of lava due to these. So these large quantities of CO2 were released thanks to the lava outpours, and hence they caused the climate to warm to that degree in order to support those different things. All right, so among the most persistent hypotheses for climate change have been those based on the idea that the sun is actually a variable star and that its energy output varies through time. So the effect is pretty obvious. The increases in solar output will result in warmer climates, and then the reductions in solar output will result in cooler climates. So this idea is obviously very appealing because it can explain climate change of any length or intensity, really. But unfortunately, there are no major long-term variations that have been yet measured outside of our atmosphere. So only until satellite data became available were we able to measure the solar output. But we've only had this type of technology for a few decades. So in order to test these hypotheses, we need records from many more decades to see if this would be plausible. Some other hypotheses are related to the sunspot cycles. So sunspots are the dark blemishes on the surface of the sun that you are seeing, for example, right here or right here in a different light. So these are huge magnetic storms that extend from the sun's surface deep into the interior. Much of the material that is ejected from sunspots, if it reaches the atmosphere, is associated with the aurora borealis, for example, or the northern lights, which is pretty cool. Sunspots actually occur in cycles, so the maximum number of them appears every 11 years or so. So during periods where there are more sunspots, the sun emits slightly more energy than during periods where the sunspots are at a minimum. The variation here seen within this cycle is of 0.1%. So although the variation in sunspots is apparent and we can date it and we can see it, the change is so small and so short that it does not seem to have an appreciable effect on the global temperatures. But again, there is a possibility that the long-term variation in the solar output does have an effect on the Earth's climate, but we just don't have enough data to prove this a plausible hypothesis yet. Okay, so in the past few slides, we have looked at potential causes for climate change that are all natural. Now we're going to go ahead and look at and examine, I guess, how it is that humans may be contributing to climate change. So the two main impacts that we seem to have are from the addition of carbon dioxide and of human-generated aerosols to the atmosphere. So there's plenty of good evidence that humans have been modifying the environment over extensive areas for thousands of years, not just in the last few centuries where we have seen this rise in industrialization. So the use of, for example, fire, as well as the overgrazing of domesticated animals, have reduced the abundance as well as the distribution of vegetation throughout the globe. And by altering the surface, humans have been modifying important climatic factors, such as the albedo of those surfaces. such as the evaporation rates that are associated, and such as the surface winds that happen. So carbon dioxide itself makes up about 4 parts per million, or 0.04% of the gases that make up the clean and dry air. But despite how small that number may be, again, it's going to have very large implications meteorologically speaking. Remember that the atmospheric carbon dioxide is basically transparent to the incoming solar shortwave radiation, but that it can act as a reflector to a certain degree to the outgoing long-wave Earth radiation. So by acting in such a way, it will re-emit some of the energy back to Earth. And this is why carbon dioxide, along with water vapor, is a gas that is largely responsible for the atmosphere's greenhouse effect. So the large industrialization of the past couple of centuries, though, has been fueled by the burning of fossil fuels. And it is still being fueled by the burning of fossil fuels for the most part. These fossil fuels are coal, petroleum, and natural gas, and we saw a lot of this on chapter 7. So the graph on the slide that you have right here shows the CO2 concentrations measured at the Mauna Loa Observatory, and here it measures concentrations since 1958 or so. So in the graph, we see a steady increase at an increasing rate as well since the measurements began in the seasonally corrected data line. So this would be this black line within the graph. So we see increase obviously in the concentrations, and we see an increasing rate as well. So concentrations are getting greater the closer we're getting to present time as well within a smaller period of time. The other line that you're seeing, so the red line right here, shows a yearly cyclicity to the carbon dioxide. So it's representing the seasonal changes that occur, and these happen when the vegetation of the northern hemisphere is more active and when it kind of dies. So when you have the vegetation of the northern hemisphere actually being active and respirating during the spring and summer months, it will absorb the CO2 from the atmosphere in order to undergo the process of photosynthesis. The increase of CO2 that you see later in the fall and in the winter is caused by the decomposition that happens from the dying parts of the vegetation. So the leaves and the branches that fall decay and then decompose, and hence will release some of that CO2 that was within their system back into space. So as humans, we also add CO2 to the atmosphere by the clearing of the forests, especially the clearing of the tropical forests. So tropical lands contain much more organic matter in the soils than do non-tropical lands. So this will in turn have a lot more carbon within the organics, and this carbon gets released to the atmosphere and becomes CO2 once the organics are burned. So much of the tropical forests of South America, Africa, and Asia are actually disappearing due to the poor logging operations, or because the owners of said lands needed them to be used for ranching and agriculture, or sometimes for mining operations as well. And although the rate of deforestation has decreased over the last 2 decades, about 25 million acres of tropical forests were permanently destroyed between 1990 and 2000, I believe, every year. And although, again, the rates of deforestation have decreased, the destruction does continue up to this date. The latest destruction, I believe, has been happening due to the growth of palm oil, which these palms have been growing or have been made to grow in a lot greater fashion. So all of the more native vegetation has been eradicated, has been burned away in order for these plantations of palms to take place.